a quick supplemental lesson to get you a little bit more acclimated with the ratio box. From this point on, the ratio box is going to be used in abundance. We're going to use it a tremendous amount, starting with ratios and percents, moving into proportions and then probability, similar figures, scale models. All of these things have a proportional relationship which use multiplicative relationships. So, what is a ratio box and why should I use it? Well, first of all, 7th grade math is loaded with relationships that can be compared multiplicatively. When I say multiplicative, I mean using multiplication and or division. If you can relate something with multiplication, you can also relate it with division. So it's an and or relationship. Generally, you pick the one you're more comfortable with. Ratio boxes allow you to visualize these relationships both within and between related quantities. So, here's a very general, very basic ratio box in which I'm going to show you the relationships. Now, think about customers in the city riding a bus, okay? Yesterday, that's what the Y stands for, 5 paid cash out of 10 total who rode the bus. So if today 60 people ride the bus, how many, based on yesterday, could we expect to pay cash? Now, if this was a ratio relationship, which it is in this case, we could find multiplicative relationships both within and between yesterday and today. So first, you may notice that 5 and 10 have a very comfortable multiplicative relationship. Well, to get from 5 to 10, we multiply by 2, right? And we can show that multiplicative relationship right on the outside of the box, being sure to note which direction I'm moving in. So if I'm trying to find out this number, though, moving from this number to that number could be a bit challenging. But I know if I'm going in multiplication in this order, the opposite, inverse operation of multiplication is division. So, if I multiply by 2 in this direction, I'm going to divide by 2 in the opposite direction. And I would just show that there, and 60 divided by 2 is 30. You probably had that figured out mentally for yourself, but the relationship is so important, and it's so important to see it on your paper. Prove it. Be able to justify your answers by showing that relationship. Now, that's not the only relationship we see in the box, and that's what makes the box so cool, is that you don't have to go just vertically. You don't have to go within yesterday and within today. You can go between them. We can go between them. Can't I multiplicatively get from 10 to 60 times 6, right? 10 times 6 is 60, so 5 times 6 is, of course, 30. And we don't have to do this because we're not trying to solve, but isn't the opposite of multiplication division? Yes, what is 60 divided by 6? 10. And 30 divided by 6 is 5. So you're going to notice these relationships in all directions, both horizontally and vertically. I'm going to load you up here with a few examples of where you might run into some of these ratio relationships and therefore use the ratio box. How about mixing pancake batter? What if you had some pancake batter, some Bisquick, for example? I put dry mix because, you know, copyright. What if for every 1 cup of dry mix that you needed 1/3 of a cup of milk? And if you have 1 serving for this much, well, what if you were trying to make 3 servings? I'm assuming that 1 serving would be, and if 1 serving is 1 cup of dry mix, then 3 servings is probably 3 cups of dry mix. So let's look at the relationships, right? Well, from 1 to 3 is a multiplicative relationship of times 3. So if I multiply by 3 going in this direction, I'm going to multiply by 3 going in this direction. And 1/3 times 3, well, think about this. If I have 1/3 3 times, I have 1 whole, yes? Also, let me show the multiplication here. 1/3 times 3 is 3/3, which is in fact 1. So 1 cup of milk. Correct? Yes. You could take that 1/3 cup and fill it 3 times, or you could just fill the 1 cup up once. Either way, it's going to work. Okay? But not only do I have this horizontal relationship, I have a vertical relationship every single time. How do you get from 1 to 1/3? Divide by 3. And so isn't it obvious here? Divide by 3. Divide by 3. Look at, see how it works? 3 divided by 3 is 1. It's pretty, right? Yes. Here's another example. What if we're working with free throw percentages? I was just watching a women's basketball game this weekend where Rutgers, they said, was terrible from the free throw line. As a team, they shoot 62%. Yes, that's terrible. Interesting, isn't it? So 62% is a ratio of what they make out of 100. If they were to take 100, we would expect them to make 62 of them. So I use the ratio box and I put in my percent. We've done this before, part to whole, right? So this column is the percent, which represents made over taken. The number of free throws made compared to the number taken. So how many would we expect them to make if they took 10 free throws in a game? Well, we try to see a relationship. This is not a beautiful relationship. We could do it. But this is much nicer. Yes? So how do you get multiplicatively from 100 to 10? You divide by 10, yes? So I'm going to draw my arrows. Divide by 10. 100 divided by 10 is 10. Well, 62 divided by 10 is 6.2. Now, I don't know about you, but I have never seen anybody make 6 2/10 free throws, ever. So my guess is, what would an appropriate guess would be 6 free throws. Okay? That's a good guess. This is the right answer mathematically, but remember, when you're answering an actual question about things that perhaps don't have parts, like free throws made, you either make it or you don't, or people. You either have a person or you don't. You don't have half of a person. You don't have a tenth of a person. You have to take your mathematical answer and say, does this answer make sense? Or what do I have to do to this answer to make it fit? Okay. Here's another one. We may have common comparisons between things like boys and girls. So here's a ratio you're given. For every 60 boys, there are 80 girls. So I've set up this ratio box because the question that it asks me is, how many boys are in a class of 30 students if we have the ratio 60 boys to 80 girls? Well, boys to total then would be 60 plus 80. 60 boys out of 140 students total. So then that means there are, if we had 30 students total, that would go there. So we're trying to find this value. Well, you know what I notice about this? I don't have to work with these numbers specifically. I can, but I don't have to. I see an interesting relationship here. I see 60 and 80 as 3/4, 3 to 4. Can that simplify 60 to 80 down to 3 to 4? If you divide it by 20 each, right? So yeah, so I'm going to kind of fill that in here also and see if there's anything I can work with comfortably. I think so. So how do I get from 4 to 3? Well, what do you think we do? That is not a multiplicative relationship that we're super comfortable with, is it? But let's think about this. 4 times something is 3. 4 times what? Well, if I multiply 4 by something, that something, in order to get 3, has to be less than 1. We've talked extensively about this. So 4 times something equals 3. Well, what is that something? Do you see that one-step equation there? You can solve for that something by dividing by 4. So x is 3/4. So this number times 3/4 is going to get me this value. 30 times 3/4. So I'm going to do that right here. 30 over 1 times 3/4 is, well, I can simplify here, 2 and 15. 15 times 3 is 45 over 2. 45 divided by 2 is 22 and a half. 22 and a half. Does that make sense? 2, 3. Oh, I used the wrong ratio. That's my fault. Time to fix it. Kimball made a mistake. Okay, so if this is 3 to 4, then 4, 5, 6, 7, this is 7, not 4, because we're talking about total. Total. I was reading it wrong. I was doing boys to girls, and that's not right. So this is 3 to 7. Okay, back it up. When you catch me, you'll really enjoy this part of the video. Okay, so 7 times what is 3? We're going to go back. 7 times what is 3? Now we can solve. Divide by 7. So 3/7. There we go. That's going to make so much more sense because it needs to be less than half of 30, and it wasn't. So I was really confused. So in a class of 30 total, how many boys will we have? 30 times 3/7. That's more like it. And that does not simplify, so I have 90/7. And when I divide 90 by 7, that's 1 and 2, 6, so 12.8. Okay, 12.8 boys, not realistic. What would a good guess be? About 13. So 13 is my solution. When I saw this answer, do you know why it didn't make sense? Do you know why? It's important to note why. Because 60 is less than half of 140. Half of 140 is 70. And so because 60 is less than 70, I know this number has to be less than half of 30. Half of 30 is 15, so it has to be less than 15. When I got 22.5, that's why I sat there and I was like, that doesn't make sense. It's true. So, I should follow my own advice. Pay attention to what you are given compared to what you are being asked for. If you are asked about boys to total, make sure you're using total. So in this case, when I did my little simplifying, is 7, not 4. And then label your boxes. Boys to total. This would be whole school, and this would be one class. Lastly, just like we just saw, relationships aren't always perfect and beautiful. Here is an example. If you had 8 questions on a quiz and you got 7 right, well, that transforms into a grade, which is a percent, which is out of 100. So 100 would represent the total. 8 does not evenly go into 100, and 7 and 8 don't have a beautiful relationship. 7 doesn't go into 8. So we need to find out what percent that would be. Now think about this for a minute. If you got 7 correct out of 8, you deserve a pretty decent grade, right? 4 out of 8 would be a 50%, so it's going to be significantly higher than that, but it's not going to be a 100%. So we think, just like we did on that last page, but this is more formal, 8 times what is 100 if I'm going in this direction? Well, 8 times something equals 100. It's not a whole number, but it's going to be a number that's got some decimal points, some decimal places to it that are other than 0. So 8 times something is 100. I set up that equation, solve it. And x, that something, is 12.5. So 8 times 12.5 is 100, which means 7 times 12.5 will give me my answer. Okay? And 7 times 12.5 is 87.5. Again, a pretty decent grade, right? But not a 100. Way better than a 50, though. Okay? So, but that's not the only relationship we could use. We could use this relationship as well. And if we're trying to get from here to here, we can think, well, 8 times what is 7? So if 8 times something is 7, that's 8 times something is 7. When you divide by 8, that something is 0.875. So if I multiply 8 by 0.875 to get 7, I can multiply 100 by 0.875 to get this answer. And if you don't think that makes sense, have a look at that. We've got 0, 0, 5, 0, 0, 7, 0.008, add it all together. Whoops. 5, 7, 8. How many decimal places? 3? Whoa. 0.875. What did I do this time? Times 0.875. Oh, 3 decimal places. Huh. I was counting 2. Okay, 87.5. Wacky day, huh? Okay, so there you go. You do get 87.5. I counted 2 decimal places instead of 3. So in this case, both of these relationships work. Obviously, if you're not paying attention to what you're doing, you're going to make mistakes. So learn from me in this case and keep track of your work. And you will see that ratio boxes are your friend.